Okay, this video is going to be about algorithms and algorithm efficiency. We're going to take a list of random numbers and sort them. Sorting is a very common problem in computer science. It's estimated that a majority of computer time is spent sorting data. And sorting it can be sorting numbers from lowest to highest. Sorting can be alphabetical sorting. You can sort by dates. When you look things up, it's important that things are sorted so you can actually find the data you're looking for. If you can imagine a list of phone numbers, like your contacts in your phone, and you wouldn't be able to find anything if there wasn't some mechanism for sorting it, either alphabetically or by the area code or something. So sorting is a huge part of what computers do. The vast majority of computer processing power is spent on sorting things. And the efficiency of the algorithms used to sort is a key component of computer science, theoretical computer science especially. Determining algorithms that are time efficient means it's a measure of the amount of time an algorithm takes, so you can solve the problem quickly. But there's also different types of efficiency than time. There's space efficiency. That's the amount of memory an algorithm needs to solve a problem. And there's complexity theory, which is basically a study of algorithm performance based on cost functions. We're just going to touch on this a little bit, but the time efficiency is mainly what we're going to focus on, because the faster the algorithm is, the more time the user has to do other things that are important in their lives. Right? We use computers as a tool to simplify our lives, and if we make our algorithms efficient, then we have more time to do the things that are important. Okay, so this website here, I'll post on the lecture video. It's got a nice introduction to algorithms and data structures. You can think of an algorithm as like one of our functions, but an algorithm is basically a series of steps or rules for solving a computational problem, right? And you can apply this to everyday activities, like this is like making coffee. So if time is 7 a.m., then we get the coffee maker and call the boil water function. If water is boiled, then add coffee and then pour coffee. Otherwise, don't do anything, right? So that's just an example of, this is like pseudocode. It's not actual JavaScript or anything. But it's a series of well-defined steps that you can perform one after the other to solve a problem. And this is what computers are really good at. They shine at, if you tell them exactly what to do, they can do it very quickly. So our job as a computer scientist is to write out the code to accomplish the task that we want the computer to do, right? And so we have to speak the computer's language, and we have to figure out how to make it the most efficient algorithm possible in order to save time and resources. Processing power these days, you can buy on Amazon Web Services, for example, you can buy processors monthly, and you get charged based on how much processor usage. So processing power is a real commodity, and it's quantifiable in terms of dollars and cents. So the less computational time we spend doing something, the less it costs. Okay, so sorting is kind of the basic example of how to get started with algorithms and their efficiency. So we're going to do a selection sort. But first, we have to basically get a data set. Okay, so we're going to start with an array. We'll call it unsorted data. Okay, and we need to add items to this data set. Okay, so I'm going to start with it empty, and I'm going to make a list. I'll make a for loop for variable I is our index. I equals 0. While I is less than, we're just going to sort 10 numbers to start with. While I is less than 10, increment I plus plus. Okay. And I can add elements to an array with the dot push method. So I've defined an array up here, it's just empty. We'll do a console log unsorted and then unsorted length. Okay, we'll see that it's empty, and then we'll go through here and we're going to add elements to it. Unsorted dot push adds an element to the end of the array, and it'll change the length value as well. Okay, so what element, what number? If I just do zeros, we'll start with that, and then I'll log it again, and we'll see we should have 10 zeros after this in our array. Okay, so we can type node, and this is called selection sort. Okay, so initially, here's the whole array, it's empty. This unsorted dot length is 0. Then we go through this for loop. We create an index at 0. This is the initial expression. This is the check every time through the loop. If this is true, we execute the code in the loop. If it's not true, we break out of the loop. So if this becomes false, we break out of the loop. I starts out at 0. Is it less than 10? Yes. Do the code and then add 1 to it. Is 1 less than 10? Yes. Do the code, push a 0 onto the end of the array, and then add 1. Is 2 less than 10? Yes. Keeps going until we get to 10 less than 10. Is 10 less than 10? No, it's not. So we do not do the code in here, and we move on outside of the code block to the next line. At this point, unsorted is an array that has pushed the number 0 onto the end of the array 10 times. Okay, and we can see unsorted.length is 10. Okay, so sorting an array of numbers that all equal 0 is pretty easy. It's already sorted. You know, they're all 0. So what we want to do is we want to make some random numbers. Okay, so we're going to make these floating point decimal numbers. So there's a built-in object in JavaScript called math. We used it once before making circles with Canvas. You use math.pi to get 3.14. There's also a function called random. Okay, and this generates a random number between 0 and 1. Okay, it's a decimal number. Alright, so let's run this code again. Now here's our array. You notice there's these random numbers in here, and they're not in any particular order. That's the idea. This is actually not truly random in the sense mathematically. Truly random numbers are expensive to get. They're very difficult. These are what's called pseudo-random. We use a mathematical algorithm that simulates randomity. It behaves mathematically similar to what actual random data behaves. Okay, so this, for all practical purposes, for what we're doing, this is random enough. Okay, so we are just selecting 10 random numbers between 0 and 1. Okay, we got these decimal numbers. So what we can do is, it's a little bit nicer if they're integers, so let's make them integers between 1 and 1,000. Okay, so here var is our number, or num is our variable that's going to hold our number, and we put this math.random here, and then we push whatever number that is. Alright, so let's do that. Okay, same thing. Notice the numbers are different this time. This was 0.87, 0.35. Every time we run it, it's different. Okay. Alright, now we want to make this number, instead of a number between 0 and 1, we want this number to be an integer, and we want it to be between 0 and 1,000. So the first thing we can do is say num equals whatever it did before and multiply it by 1,000. So what that's going to do is move this decimal place over, right? So it moves this decimal place over 3 digits. So this one would be 16 point something. Okay. So let's see what we got here. Okay, so all these numbers are between 0 and 1,000. Right? So that's good. But now we need to truncate the bottom, or we can round them. So we should take the floor. What we're going to do is just take the floor of the number. We'll remove the decimal completely. Okay, so math has the math object. It's a capital M, and it's built in to JavaScript. You can access it just by typing math with a capital M. It has another function on it called floor. So you can say number equals math dot floor of number. Okay, so that has removed all the decimals. And so you notice these numbers are all between 0 and 1,000. Multiplying by 1,000, just move the decimal point 3 places. Okay, so that one would be 72, this would be 168, this would be 702, right? And then math.floor truncates the decimals off of it. Okay, and we can see this. We could make a list of 100 numbers just by changing this for loop. This is the condition that we check to see if we keep running the loop. So it was 10, so it would run 10 times, and then I just added a 0. Now it'll run 100 times. So again, all these numbers are between 0 and 1,000. Run it over and over to see. Okay, so that's what we're looking for. Okay, so let's put it back at 10 so we can kind of see what's going on. Alright. So, what we want to do is we want to sort these numbers. Okay, and this is going to get into the time complexity. The time complexity depends on how many items you're sorting. Obviously, if you're sorting 10 items, that's a whole lot faster than sorting 100 items or 1,000, right? So this is, we're sorting in items. Okay, so I'm going to define some value of n at the top. Var n equals, and we're going to call this 10. So if we want 10 numbers in our for loop, instead of putting in the number 10, the 10 literal, we're going to put in the variable. And so now anytime we reference the variable n in our code, that's the same number here. That's the same number of items we're adding to our array. Okay, so if I make this n equals 2, we can see the array should have 2 values in it. Sorting n equals 2 items. Okay, so we'll say n equals 10 again. Okay, so selection sort, basically you go through the list of items. You start with the first item, and then you iterate through the rest of the items, and if one of the items is smaller, then you swap them. Okay, So here we start with 728, and is 526 smaller? Yes, so we swap it. Then we go to 813. Would 813 be smaller than 526? No, so we move on to the next one. 918, no. 75, yes, so then we swap it. Okay, when we get through the first pass, the smallest number of all of these n items, there's 10 of them, n equals 10 in this case, the smallest number in the list should be in this first place, because whenever we found a number that was smaller, we swapped the values. Okay, so we went through the list, so we executed n instructions. Okay, so let's do this. The second time through the list, we no longer have to do this one. We need to compare this value to the rest of them and get the smallest one of the remaining items in the list. And by the end of going through all of those items, the second number should be the second smallest in the list. And you keep going on that pattern. Okay, so we make a for loop for our I equals 0 while I is less than n I plus plus. Okay, so our first number, so this is our target number that we're looking at. Target number. So in the first pass through, it's this first number. And we'll call it smallest. Alright, smallest number is going to equal our unsorted array at index I. So I starts out at 0 and it increases to 9. 9 is the last element. The length of the array is 10. 10 minus 1 is the index of the last element. Okay, so the smallest number position is I. So this is what we're starting with. Now we make another for loop. This is called nesting for loops. For j equals I plus 1, because we don't need to compare this number to this number, because if you swap them they're the same. So we don't even bother with that one. We always skip on to one past it. Okay, so for variable j is always going to equal whatever I started out as. So first time through the loop I is 0. We're looking at the first item. So j is going to start here and go all the way to the end of the list. Okay, let's say we're at the third time through the loop. I is here, so that would be I equals 2. J is going to start on I equals 3. So if I is 2, j starts out at 2 plus 1, which is 3. Okay, so j always has to start one more than I starts out as. So this is the initialization for our j. So our index is whatever I is plus 1, while j is less than n, which is the number of items in the list. Right? While it's less than 10, we add 1 to j. J plus plus. Okay. So, if unsorted j, now remember, we're starting out here, I is 0, so j the first time through is this. So if this number, unsorted j, we're using the j index to access this number, if that's less than what we have stored in smallest, then it's not actually the smallest. So we need to say smallest equals unsorted j. We'll make a temp variable, or temp equals smallest. So this was the previous smallest. Or no. Here we go. Smallest equals unsorted j. So we're swapping the values, right? So we have unsorted I is iterating through the list, and j is always higher than I. Okay, so this is I equals 0, j equals 1. Okay, so we say the smallest we know now, so far, going through this, is unsorted j. And we know that unsorted I, which is index I, which is 0, this one, since we're sorting smallest to highest, this one should now be unsorted j. Let's comment that out. The first one should be unsorted j, so we're moving 526 here. So right now we would have 526, but then this is still 526. We haven't changed that yet. Okay. Previously, smallest, we had stored 728 in there. Unsorted I, we stored it in there, and smallest. Okay. So now we have to make unsorted j equal to smallest, because previously we'd set that value. Let's just call it target. I think smallest is going to make it confusing. Okay, so target is just, it's the active element we're looking at. First time through the loop, this is our target. This is the one we're going to swap out anytime we find a number in the list that's larger, or smaller, I mean. So we're sorting the list from smallest to largest. And the target index, the target value, is whatever's in the I position in the array. Okay, so first time through the array, I is 0. The target value is 728. Okay, we spotted a smaller value here at index j. So in the array, we make this value that smaller value. It's 526, but then this is still 526, so we have to make unsorted j, which is this position, we have to make that equal to what we had previously set target. And then the last set is we have a new target number. The new target number is this new this new value at position I, because we swapped them out. Okay. So another way to make this code a little bit clearer, we can say the smaller number, unsorted j, is less than the target. So the smaller number is j. So unsorted j. And we can say the bigger number is unsorted I. Okay. So I was trying to do it in as few lines as possible, but that makes it a little more complicated to understand. So I think this will be a little bit easier. So our target number, we have smaller, bigger. Okay. So in the case that the item needs to swap, we make item j the bigger number and item I the smaller number. So unsorted I is smaller and unsorted j is bigger. This is essentially just swapping these two items. Okay, so for example, if j was 0, 1, 2, 3, 4, 5, and I is 0, we say the smaller number is j, because we know we need to swap, and it is the smaller number. The bigger number is the item at index I. Now we make the item at index I, whatever that value is, we make it the smaller number. And then whatever the item at index j, we make that the bigger number. So the big number swaps over here to 31. Okay, so that's essentially what's going on here. Okay. And so we can say console.log sorted list. Let's rename this since it eventually becomes sorted. Naming is very important, so we don't get confused. Let's rename unsorted to just our data set. Okay. We go find, replace. We don't want to replace the string literal, but we do want to replace the variable names. Replace. Okay. So there we go. Our data is in a list, an array. So let's execute this. And here you see we have sorted list data somewhere. Data j is less than target. Oh, I forgot to add our target has changed, right? So our target is, we can get rid of this. It's always just data I. Data I. Okay, so basically remember, j is always an index higher than I. So if the item in the array higher than wherever I index is, if that's a smaller number, then we know we're going to have to swap them. All this does is swap the two numbers. Okay, this determines if we should swap. Okay, so if the item in index position j is larger than the item in index position I, then we swap. Or smaller than, because we're sorting from smallest to largest. Alright, run the algorithm, and we have 10 items. We've got 231, 319, 542, 542, 637, 713, 779, 805, 953, and 973, right? So they all appear to be in order now from this code, and this is called selection sort. Do it again, we get new set of numbers, new set of data. And if we want to make it more interesting, we can say 100 items. We'll see how long this takes to process. Does it pretty quickly. Look through and verify. They're all in sorted order. Right? Let's do 1,000. Did it pretty quick. Let's do 10,000. See, now there was a slight pause there. You could see it took it some time to calculate. Alright, so if we do 100,000, we can see that this is about the realm where the computer starts to take a reasonable amount of time that a human would notice. Because computers are so incredibly fast, we don't notice most of what computers do because it happens so quickly. Here we're sorting 100,000 items, and we're going to start to see it actually take the computer some time to solve it. There you go. So, what is that, 6 seconds or something like that? 100,000 items sorted. So that's actually quite a complicated task. And if you were given 100,000 numbers on a piece of paper and a pencil, that would take you a tremendous amount of time to sort. Okay, so that's why it's one of the amazing tasks that computers are really good at. It helps us locate things and store things and find things. And that's also why computers, the majority of what they do is sorting data, because it's so important for us to be organized. Okay, so this is selection sort, and going back to algorithms and efficiency, there's a concept of big O notation. Big O notation basically expresses the part of the algorithm that takes the most time in terms of n. So in terms of size of the data set, obviously a data set that's 10 elements is going to behave or be solved faster than a data set of 1,000 or 1,000,000 items. Okay, so we want to test the algorithm based on its performance, not the size of the data set. So we abstract that away and just call it n, regardless of what the size of the data set is. Big O of n tells us how time efficient the algorithm is. Okay, so constant time is big O of some constant number. That's essentially like placing something in an array, assigning a value to a variable like they're saying here. Basically one computer instruction that the processor can execute. Okay, linear time is big O of n. That means you execute one instruction for every n items. So this would be like going through this loop. We go through the loop n times, and then we add an element to the array. So this is a big O of n. Now we're actually doing several instructions here, so this is big O of 4n. Okay, but that's essentially still just big O of n. The 4 doesn't, it does make it take longer, but it's negligible. Okay, so the important bit, the part that takes the longest, is going through the loop n times. So if we go through this loop 1,000,000 times, it's more important that we're going through the loop 1,000,000 times than executing 4 instructions. So this would actually be like 4,000,000 instructions, but the important part is the 1,000,000, not the 4. Okay, so the important part is the bit that relates to the size of the data. Okay, n is the size of our data set. Alright, so that's linear time. Quadratic time is n squared. Okay, so this is what we're doing here, nested loops. Now ours is slightly less than n squared. Here we're starting I equals 0, going I goes up to n, increments one at a time. Here we start j equals 0, go up to n. We didn't quite do that. We didn't start at j equals 0. We started at j equals I plus 1. So it's n squared minus n, basically. So, but that's essentially still n squared. So the important part is the time complexity in the algorithm that has the most impact on how long it takes. That's what the big O notation is. It's big omega. Okay. So you'll see this a lot if you're in computer science. We're just basically touching on it here for you to get some exposure to it. But if you take an algorithms class or data structures class, there's going to be a lot of talk about efficiency, time efficiency, and space efficiency. The big O algorithm is very important. Okay, so here's some common things that happen in n-squared time: forming a linear search in a matrix, time complexity of, there's different types of sorts. I showed you selection sort, and there's quick sort, and there's several other things. Logarithmic time, log of n, that basically happens anytime the loop size is multiplied by 2. So normally we do like I++ here, Instead, we multiply the index by 2. So instead of going 0, 1, 2, 3, 4, 5, it goes 0, 2, 4, 8, 16, doubles in size every time. So you run through the loop much faster because you're skipping so many elements. I still stops at 1, but first time through is 0 or is 1. It should actually be 1. And then second time through it's 2. And the second time through it's 4. We skipped the 3. And the next time through it's 8. And we skipped 5, 6, 7. The next time through 16. We skipped practically half of them. So every time you're skipping a whole bunch of the iterations in the loop. Okay. So this is a much faster algorithm. O log of n is much faster than O of n. And it's much faster than O of n squared, which is quadratic or often called polynomial. So if it's n to the third or n to the fourth or n to the fifth, that's polynomial. Okay. So logarithmic time is common for binary search. If you have a search tree and you want to look for something, that's logarithmic time. Linear arithmetic time, it's n log n. So these are basically most of the sorting algorithms that are efficient. The average case or the worst case is n log n. So that's pretty good for a sorting algorithm. Okay, but it does take a long time because it does depend on the size of the data set times a little bit more, log n. Okay, and then you can also have exponential time, which is big O of some constant value to the nth power. And that is really inefficient. That's extremely inefficient. But some problems are so complicated that you need that amount of time. Okay, so this is just a quick introduction to big O notation. And so basically going through this one, we're going through a for loop n times, so we're at big O of n. But each one of those times, we're going through n minus 1 loops. Okay, so this starts at 0, goes to n, that's n times. This starts at n minus, or it starts at 0 and goes to n minus 1 essentially. So it starts at 1. So this is big O of n times n minus 1, which is big O of n squared minus n. Okay, and minus n. And so with big O notation, you don't really care about this because it's much smaller than this. Okay, so this simplifies down to big O of n squared. So that's the efficiency of this particular algorithm. It's a pretty easy algorithm. There are much more complicated algorithms that, as I said before, can go down to n log n. That's about the most efficient. You can sort large data sets, and it's about the most efficient time complexity you can get. Okay, but this one is very simple to code, so that's a nice thing about this one. Okay, there's also, depending on the size, the way the data is set up, it could be randomly the data is already in order, right? Certain algorithms are better in that case scenario. So there's a best case and a worst case and an average case for all of these. But big O generally is talking about the worst case scenario, the most time it would take for this algorithm to complete. Alright. So that is selection sort and big O notation.